Hey, it's Nathan, and today I wanted to give like an intuitive overview of what I do for research and then also talk about probably like a small example of something that I work on. That isn't really what I work on, but it's like related. In fractal geometry, nowadays, we've kind of realized that Hausdorff dimension doesn't do it. It just isn't good enough because it's has a lot of these like properties that aren't nice. Say that part of your set is the Cantor set, which has a particular Hausdorff dimension that's less than 1, and then you have another piece of your set that looks like an interval that has Hausdorff dimension 1. The Hausdorff dimension is going to evaluate the entire Hausdorff dimension of that union of stuff as being just the largest thing, that thing that looks like the interval. And so Hausdorff dimension isn't really fine enough, or it doesn't have enough detail to it in order to describe the complexity of some of these things that we care about in fractal geometry. In modern fractal geometry, a lot of times we're concerned with objects that are generated by iteration. So in fractal geometry, there are sort of two flavors of this. There is iteration by a discrete sort of map. Think of like things like the Sierpinski triangle or the Cantor set. And then the second example that I'm not going to focus on in this video is that of iteration of functions. So fractals that are things that we care about in fractal geometry that fall under this class would be things like the Mandelbrot set, which is the set of just like C within the complex numbers such that the limit as n goes to infinity of the absolute value of, or the modulus rather, of the iterates of f sub c to the n of 0 is less than infinity for every n within the naturals, where f sub c of z is equal to z squared plus c. I'm not going to focus on that. If I said that too fast, that's fine, because it will not come back up in this video. Yes. So the two examples that I've provided are not like that problem that I've mentioned. The Sierpinski's triangle and the Cantor set are highly regular examples of this like self-similar type thing that we describe in fractal geometry. There's also some uniformity to their construction, and you might be sitting there going like, Nathan, you're missing the point. Fractals are supposed to be self-similar. That's what fractals do. And to that I say no, because fractal doesn't have a definition. It's not a well-defined term. It doesn't really mean anything in math. A lot of times we say it in abstracts, but it never comes up as a definition in the paper, right? So even though these particular two examples of sets that we would want to study in fractal geometry have nice properties that we commonly associate to quote-unquote fractals, or sets that we would like to study in fractal geometry, they're not all of them. And so I should give you an example of how a set might be construed as irregular. And I'm not going to do this by like constructing one that's irregular. Instead, I'm going to do this by taking one that's regular and distributing something on it in an irregular way. You can do this in general by just letting J be a limit set and some process, and then let me be a Borel probability measure supported on that limit set, or possibly a subset of the limit set. The example of that generality that I want to talk about is that of the middle third Cantor set. So you take the middle third Cantor set and you have a symbolic representation of it, which last time I talked about this, I used zeros and twos. In this one, we're just going to replace the twos with ones for simplicity. So we can symbolically identify it with infinite sequences of zeros and ones. And at finite levels of the construction, we define the measure in the following way. So the measure where the sequence starts with a 0 is going to be p. The measure where the sequence starts with 1 is going to be 1 minus p. And then we extend that measure by setting the measure of a finite sequence of symbols at the beginning is equal to the measure if the finite sequence of symbols was that first thing times the measure if that finite sequence was the second thing for every pair of finite strings of symbols of zeros and ones. So in particular, if p is 1/3, then the probability of the set of stuff that starts with 0, 1 is going to be the probability that it started with 0 times the probability that it started with 1, which is equal to 1/3 times 2/3, which is 2/9. Now you can think about this measure as distributing mass across the limit set. So in our particular example, if we have p equal to 1/3, you sort of get a picture of what follows. So at the first level of the Cantor set construction, all of the mass is uniformly distributed across the unit interval. So after you iterate the process of developing the Cantor set, because of how the measure is defined, the mass is going to be non-uniformly distributed amongst the pieces. So 1/3 of it will end up in the first piece and 2/3 of it will end up in the next piece. And then after another iteration, you'll have 1/9 in the first piece, 2/9 in the second, 2/9 in the third, and then 4/9 in the fourth. And you can continue doing this construction over and over again. And the more ones that you choose in your digital expansion or your representation of things in the Cantor set, the more mass is concentrated at that point. So this is what we call the local dimension of a point with respect to a measure. What you do is you go ahead and you look at the ratio of the log of a measure of a ball of a certain radius over the log of that radius. And you take that limit as r goes to 0. In this particular case, at 1, which is just going to be in terms of the Cantor set, 1 is in the Cantor set, it's 1 repeating, it's the sequence that has all 1s. So you're always choosing to go to the right, you're always choosing to distribute more mass to that piece of the construction all the way down. You can show that the local dimension with respect to this measure at 1 is going to be equal to minus log of 1 minus p over log 3. And then at 0, where you're choosing to distribute less mass at each point in the construction, you're going to have the local dimension of 0 with respect to mu be equal to minus log of p over log 3. The important thing here is that the mass is distributed in terms of this dimension analysis in different ways. Locally, 1 looks like a different thing from a point of this local dimension than 0 does. So I'm halfway through recording this video and I'm realizing that I said I would do this at a high level, like a general intuitive level, and I'm not, because curse of knowledge. But I guess for me, this is the high level intuitive version. So here we keep going. And so the question that you can ask is, well, like, how do you study this irregularly distributed mass? How do you study this measure on this limit set? And what you do is you go ahead and say, okay, well, I already know that I have for this irregular measure, I keep saying irregular measure, but regular is a defined term in measure theory. I'm not talking about that type of regular. I just mean in terms of like mass is not evenly distributed. So like non-even measure might be better, but anyway, continuing. So what you know is that we already know that different points can have different local dimensions with respect to this measure. And what we can do is we can then go ahead and say, okay, well, I'm just going to collect together all of the points that have the same local dimension and call that a piece of the set. What's nice about doing this is that you've gone ahead and taken your limit set and you've partitioned it into these sets that have a particular property, where locally, with respect to whatever measure that you're using, they look the same at all points within that particular piece of the decomposition. We call this collection of sets the multifractal decomposition of the Julia set, or the limit set, whatever you're working with respect to the parameter that you're using. So with respect to the mu local dimension here. And so what we do when we do multifractal analysis is that we study this function, which we call, I guess we'll call it f of alpha, which is defined to be the Hausdorff dimension of the big F's of alpha piece, or I might have written J sub alpha piece of the multifractal decomposition. We want to know how that function works as your alpha parameter varies continuously. And this function is called the multifractal spectrum of the limit set J with respect to the parameter. So with respect to the mu local dimension. When you do this, right, you have all of these questions. You now have a function. It spits out a Hausdorff dimension. Hausdorff dimension is this really like weird thing to calculate a lot of the time. Can you say things about this function? Is it continuous? Is it differentiable? Is it analytic, where you have derivatives forever? Can you find places where it has an inflection point, like other graph sketching analysis that you would do in a calculus 1 class, honestly, right? And we do these things for these different limit sets and different measures to try and understand the different properties of these fractals at a local level, right? So we concern ourselves with this multifractal spectrum. And in the example I gave in this video for the irregular measure, or the not even measure rather, which is what I should say, where P is just not 1/2, you can go ahead and show that you get the following information out. And this derivation is done in Falconer's fractal geometry textbook. I don't want to go through the whole process just because, but it is a thing that you can do. And I believe in this case that the spectrum is really analytic and like has all these really nice properties that you wouldn't expect from a function that's defined by a Hausdorff dimension, right? Again, Hausdorff dimension is this really weird thing that's defined by a limit of an infimum over these things called delta covers, where you don't have strict control over the size of the cover, you just, or rather of the size of the cover element, you just have control over the maximum size a cover element can be in terms of diameter. There are all these connections running around. And a lot of times we study this in the context of dynamical systems or places where you have this like symbolic representation where you can pull whatever set you're working on up into a dynamical system where these things also have dynamical interest as well, where like certain parameters have different invariance properties and whatnot. I need to stop because I have said, I think, too much and also too little all at the same time. That's what I think about. That's what I work on in my research. Anyway, that's it. If you enjoyed this video or want to see me talk about more math stuff, probably, hopefully, in more rigor next time, I have more videos on here where I talk about things in better detail than I did in this video. Also, if you're interested in like Mac academia or like grad school and things like that, I have done some updates on my graduate process in various places on this channel as well, so those are there too, so you can subscribe for that. If you enjoyed this video, give it a thumbs up, and if you want me to talk about certain topics in particular, or talk more about this, or have questions for me about what I do, or anything like that, you can comment them down below. But yeah, as always, I'm Nathan, this one was Chalk, and I will see you next time.